Kia ora and welcome to Forest Call for this week, the program dedicated to telling the forest story. I'm Don Carson. Today we head off out of the forests and off to some tall timber of another sort. Wooden construction for high rise. It was once that going up 2 stories with a standard weatherboard bungalow on a slope was as big as timber ever got. Above that, and it was all steel and concrete. But now, with modern engineering and some products such as laminated veneer lumber beams and cross-laminated timber panels, wood is being built high all around the world. Here's an information dump for you. Take the stats. The Sumitomo building in Tokyo is going to be 90% of wood, 184,000 cubic metres of it. But get this, it's tall, 350 metres high. It'll cost 8 billion New Zealand dollars equivalent when it's finished in 2041. But in Christchurch, there's such an engineered wooden building much closer to completion. So I went along to Canterbury University to see this example of modern construction. It's the Beatrice Tinsley building, and have it explained by pioneer engineered timber advocate Andy Buchanan.
Well, what we've got here is a 4-storey timber building, and this is a modern earthquake resistant timber building here on the campus of the University of Canterbury, and this has got all the latest technology in it. And this building is a low damage building. If there's an earthquake, the building can move, but it'll snap back into position.
How is that done then?
This is my giraffe, and what I'm suggesting is that we could build a building that acts a bit like this giraffe, so that if an earthquake comes, it snaps back into position. This giraffe is being held together by rubber bands that make it snap back into position. And in this building, the rubber bands are not made of rubber, they're made of high strength steel, and here they are right here.
How new is this technology, Andy?
This technology was developed in the concrete industry 10 or 15 years ago. It then was adopted by the steel industry, and now we can do it in wood. And so the research that we've done right here at the University of Canterbury has shown that anything we can do with a steel or concrete building, we can do in wood. And here's an example of it right here. There was an old building here. It was damaged in the earthquake. It was knocked down, but they didn't want to dig up the foundation. They wanted to reuse the foundation, so they needed a lightweight material, and this timber building is lighter weight than steel or concrete. Another reason they built the timber building here is that this building uses the technology which was developed here in the School of Engineering, and the university wanted to show off this technology and show what was possible because they had developed the technology over the last 5 or 10 years. All of the wood in this building is what we call engineered wood products. So the trees, after the trees were cut down, they were cut into small pieces of wood, glued back together to make massive beams and columns. A building like this will have 1,000 cubic metres of wood, and if we built more buildings like this, we wouldn't have to export all our logs to China.
What sort of timber engineering is there? It's not all one type of technology.
We've got the gluing and processing technology for gluing small pieces of wood into big pieces. We've got the fastening technology. We've got screws and bolts and the steel cables for clipping it all together. And we've also done the research so that we now know that buildings like this can resist big earthquakes or anything else that you throw at them.
We're told that this building at the top moves 400 millimetres in an earthquake. That's quite a lot of give.
All buildings are flexible and they move. They move in earthquakes, they move in the wind. And this timber building will move just the same amount as a concrete or steel building. We want it to move so it can absorb some energy and be flexible, but we don't want it to move so far that the windows break. So it's got to be designed very carefully, so it's got just the right amount of flexibility. And we can do that with these modern wood materials. This building is made of LVL, laminated veneer lumber, which is thin layers glued together. And that LVL makes things which are long and strong. But we can also make cross-laminated timber. Cross-laminated timber makes big flat panels by gluing wood together. It's like thick plywood, and we can make huge panels, and we can make a building, prefabricated building, by standing up walls and standing up floors in a big prefabricated building. I want to talk about this special piece of steel because this is a fuse that goes into this building. And this is the only part of the building that would be damaged in an earthquake, because as the steel bends, it would absorb some energy, it would be damaged, but it's not a problem because this could be replaced. If you look around Christchurch, more than 1,000 concrete buildings in Christchurch were demolished because they had damage in them, and the damage was too hard to repair. But in this building, the damage is easily repaired because we can just replace these plates. And that's what we call low damage design. The concrete guys are doing it, the steel people are doing it, and now we can do it in wood. If we want to take this steel plate and attach it onto the wood, the best way to do it is to use these high-strength steel nails. We call them timber rivets. And those timber rivets can be hammered into the wood, and they'll make a super strong connection so that the steel can't move when it's fixed onto the wood.
What advantage then is there in prefabricating this timber construction and bringing it in from another site?
To stop buildings getting too expensive, we've got to do more building work in the factory and less work on the building site. And one of the advantages of buildings like this is that large parts of the building can be pre-assembled in a factory, a wood processing factory, and then brought here to site and then stood up very quickly. And whereas a steel or concrete building, in order to make the steel and the concrete, you have to pump carbon dioxide into the atmosphere. With a timber building, the trees in the forest, they absorb carbon dioxide and they store the carbon in the building, and the carbon in this building will be there for hundreds of years.
People look at timber buildings and they say there's a greater risk of fire. What's your response?
There's always a risk of fire, and wood does burn. But this is not a building made of little sticks of wood. It's a building made of big, massive lumps of wood, and those big, massive lumps of wood just don't burn in the same way that small sticks of wood do. So a building like this will be just as safe in fire as a steel or a concrete building. We could be building hundreds of buildings like this because the cost of the building's about the same as a steel or concrete building, and the performance is the same, and people love it. The builders here love working on this building site because it just feels so good, and the people who are going to live and work in these buildings are going to love it. So we could be doing a whole lot more.
What do we have to do then to educate the architects, the specifiers and the regulators about the advantages of using this wood technology?
We want a lot more timber buildings like this, and if we're going to have them, we have to educate the architects and the engineers. And the best way of doing it is to bring them, to show this to them and to show them what can be done. And then, of course, in the universities and schools of engineering and schools of architecture, this is already happening. People are being taught how to design these buildings because it's not easy. You have to think about a lot of different factors. You've got to think about the fire safety, and the noise in the building and the durability of the building and how it all goes together. There's a lot of technology there, but it can be done, and this building shows how it can be done. We need designers who understand wood, we need architects and engineers who know what to do, and we need processing facilities, factories that can manufacture the pieces.
How would it help if the local government, central government adopted wood-first policies?
We need an incentive to get started, because once an architect or an engineer has designed the first one, then it's much easier for them to design the next one. And so to get over the line, if we just have an incentive if the client, the building owner, or the local government, as it might be, if that client wants a building, they have to ask for it, and a wood-first policy would help enormously in that, to make that happen.
And if you're curious about Beatrice Tinsley and who she is, she's a New Zealand astronomer. Here's her extraordinary life story in a book, Bright Shining Star. And that construction of her building is due for completion next year. So Bob Jones leads by example, but it's an uphill battle to convince architects and building specifiers used to designing in steel and concrete these days, despite timber being locally sourced, lighter, quicker to construct with, more flexible in earthquakes, better for carbon storage, easy to fix, and so on. In Australia, A succession of local and now state governments have gone for a wood-first policy. Rotorua Lakes Council was the only such local government to have the same policy here, but now the Gisborne District Council has also advocated for wood construction as the first option. Our planted forest industry, challenging to be our second primary export earner. Wood's environmentally good in plant and product for building and landscapes. We're great in technology and science, selecting stronger, straighter trees, safer ways to harvest them, cleaner and earthquake-resistant ways to build. Forests, regionally vital for economic development, creating all sorts of jobs. A prime future investment for our nation. Love our forests. I wasn't originally going to come here, but after talking to Andy Buchanan at that impressive construction of the Beatrice Tinsley building, I felt compelled to go and see the source of what they call big timber. So here I am at Nelson Pine at Richmond, where they make the LVL. Nelson Pine makes claim to be Nelson's third largest employer. It has 8 hectares of building and utilises 40% of the region's wood production. Its main output was medium-density fibreboard, MDF, but these days its star production is laminated veneer lumber, LVL, made by a simple process of peeling logs into great sheets and then gluing them together.
It is basically a slicing, which is a peeling, and then we dry it, we put glue on it, compress it together. It's a little bit like in a kitchen, and this is what we do.
Reglue the LVL veneers all in a single direction. So all the grain is running in the same direction. So we basically re-engineered the tree. Still the same tree, it's just improved.
We are highly integrated operations. From a forest which we operate about 30,000 hectares, we process roughly about 1 million tons or cubic meter of logs a year. A big portion of that goes into our MDF, but another main product, more importantly so in time to come, is the LVL, which then starts with peeling the logs with a rotary lathe into veneer sheets. These will then be sorted by moisture and by strength and by other aesthetical aspects into different veneer grades at the end of the dryer. Then this veneer, dried veneer, will be scarfed so we can join the veneer sheets in length. Depending on the recipes, we combine different grades of veneers into the LVL in order to achieve desired strength and meet international standards or national standards and building codes. We will pass this veneer then through a glue spreader, applying glue to a hot press which compresses the veneer sheets and applies heat and pressure so that the glue can cure and give a strong bond, which is A-rated bond in New Zealand. This means it's a durable bond. We will then use these so-called billets in parts for products like scaffolding or timber, truss and frame and formworks, and other LVL parts will be used in such respect that we will combine them to big timber, as we call it, by gluing them again together with a cold press glue, giving us another A bond, but the timber will be way bigger, up to 30 centimeter thick, 1.2 meter wide, and up to 18 meter long. These big timbers then will be processed in our added value departments, cut to size, in length, in width, and thicknesses, and will be cut into shapes, allowing for connections in big constructions like the Nelson Airport and alike.
And the Beatrice Tinsley building.
And the Beatrice Tinsley building, which is very impressive, and we just recently supplied all this to Christchurch, and as you have seen, it has been erected. With LVL, we do, I would call it standard LVL, which is basically graded by strength. It's a structural LVL, it's a structural product which goes into the construction industry.
There are 2 basic improvements on sawn timber by making it into LVL.
This allows us to identify defects and to minimize defects like, for example, knots or splits or other defects which could have an effect on the strength, which is the desired property for a construction. So we can control that and we can minimize the impact of these. So we achieve a product which is of higher strength properties as compared to a typical sawn timber. The other aspect is that it has less warp, twist, buckle, etc., etc. It's basically a straight, dimensionally very stable product, and this is a big advantage of LVL as an engineered wood over a sawn timber.
With the commercial buildings, we've proven that timber is a commercial viable with little or no cost difference. The issue is really getting the traditional marketplace over the line to say, right, I'd like to go for a timber building. We're generally finding that it's becoming a lot more client specified, that the client's saying, I would like you to look at a timber building. So we need the clients to actually first come on board and say, okay, we're keen to look at a timber building, go into their engineers and their architects and saying, right, what are the options? How is this going to work for us? Rather than just going straight down the line and saying, well, I need a building, and then everyone's just going out and designing concrete and steel, something they're used to dealing with.
LVL is a relatively new product. So the typical 2x4 timber frame construction, this is historically here in New Zealand being used by, and people are familiar, the builders are familiar with that, the architects, designers are all familiar with that type of construction. LVL is a relatively new product, developed in North America, perfected in Europe, and now we have it here in New Zealand. What is required in order to promote that product more are changes and upgrades of building codes and standards on a national level, and also to educate the users, which are in the very first place the architects and designer, to get more familiar with the potential and the capacity of LVL as a fantastic high performance product.
The architects love timber, and the engineers, it actually makes them have to work, the engineers have to work a little bit harder on it, but we find there's a whole community of engineers and architects that are actually very keen behind the timber, but it's actually getting, it needs everyone to come on board at the same time and actually say, right, okay, well look, we're keen to look at a timber building, so the architect's saying, yeah, we're keen, the client's keen to look at a timber building, the architect says, right, okay, well we have options, we can start looking down that line, and then the engineers need to get on board with the actual construction of that and think about it, because this doesn't all work the same way. We've got a 35 MPa compressive strength on the end grain, same as concrete. We've got a 10 MPa compressive strength on the sides. So you have to think outside the box how it's going to work. You have to think a lot more about the connections and how that's going to happen.
Then there's the raw material, not without its variability challenges, and that's radiata pine.
What we do here in Nelson Pine Industry, by the name as it says, we're using radiata pine grown domestically out of sustainably managed forests. So it gives us a supply of our resources basically forever.
So while the LVL process itself is quite simple, the real-time measurements of the veneer and the processing have to be very sophisticated.
So we are able to identify and measure physically the property, strength, moisture and appearance through scanning cameras and other electronic sensors. So it allows us to make an absolutely informed decisions about the specific properties of this individual veneer sheet. And later on we will combine individual veneer sheets to an overall product.
And at Nelson Pine they see overall timber properties, not just in the LVL.
For everyone it's something different, but first and foremost it is a carbon store. Everything that we do with timber, we've grown it up, it's stored carbon, and that's sitting in that building and it's staying there forever. It's better environmentally for people working in there. There's various reports talking about the benefits of actually being in a timber building. Biophilia, I think, is actually the name. So a lot of hospitals now around the world are being built with timber waiting rooms, a lot of timber cladding going in, just to actually get that whole feel for the timber side. People say, right, fire's an issue. It actually isn't. We design around fire. Timber chars rather than burns. It becomes actually, we can work out exactly how much timber will be left under a 30-minute fire, and so we know what that structure will be doing. Unlike some other materials that may actually get affected quicker or slower, if you had a timber building on fire for 30 minutes, you know that that will still be standing and it will still have a certain strength level. That's all designed into that structure. So those issues aren't Outside's an issue. In New Zealand, in particular, in an earthquake zone, if we can take out concrete from the mid-floors and we can put timber flooring systems in, we can reduce a lot of the mass of the building, which means under an earthquake, when the building's going to start rocking around, the more mass that we've got up there, the more movement we're going to get into that building.
I've been a mum, and it's kept me busy in the last 8 years. So I've just been on and off jobs, been working as bakery assistants and just agrodome and tourism and all that kind of stuff. But I recently did a course last year, chainsaw operations through Wairiki, and I really enjoyed it. Plus my partner works in forestry, so I thought I'd come back and do the diploma, and that's why I came back. A lot of family involved in forestry, family that own forestry companies like C&I, and just being out there, I just enjoyed it. I've learnt a lot about science and stuff that I didn't stay at school long enough to learn. So being here, I didn't think I was going to do really well, but I have, and the teachers have even said that to me. I left school when I was 14, so I didn't do any NZCA units or nothing, and then come here and I've been getting A+, and yeah, just been really happy with my achievements. With what the teachers have been telling us and the tutors, that there is lots and lots out there. We can go biosecurity, we can go forest manager, we can go to just running crews, and there's just lots out there. I've got 4 kids, so I'm just busy day and night. The good thing I enjoy is that I can drop them off at school and then come to course myself where I can learn, and then by the time I'm finished in the day, I pick them up and then we all go home together, and then back into my work at night. Forestry will be around for a long time, so I'm confident that my career that I've chosen will succeed.
The idea of the DiscBot was to build a sampling platform that would enable us to sample lots of trees in a cost-effective manner, so that we can sample thousands, if not tens of thousands of trees, to really build up a picture of the range of internal wood property distributions that we see in trees and what the impact of those distributions are on end product performance. So really what we wanted to do early on was understand the variation that exists in radiata pine wood properties, as well as the properties of other commercially important species in New Zealand. So starting in about the 1950s, we embarked on a intensive program of measuring wood properties using outer wood core samples, so 5mm core samples taken from the outside of the tree. We sampled probably 10,000 radiata pine trees over a long period of time, and that enabled us to understand the patterns of variation that exist between trees within a stand, but also between sites. So we learned a lot about the environmental drivers for wood property variation in New Zealand. So we see in warmer northern sites we get wood with higher density, in cooler southern and upland sites we get wood with lower density. Then we moved on to sampling with 12mm cores, and this enabled us to understand more about the variation in other properties, not just density. So we learned about the angle of the cellulose microfibers. We also learned something about the variation in wood stiffness that exists within trees. So if we look at a single tree, we see a huge amount of variation in wood properties from the pith, from the centre of the tree through to the outside. And these gradients in wood properties affect the performance in service. So some of the things that we're very keen to avoid are twist, for example, the piece I'm holding up here, but we also want wood that is stiff enough to be used in engineering applications. So one of the things we did with the DiscBot was to really intensively sample the variation that exists within a tree at a scale that would enable us to make predictions of how wood will behave in service, particularly as it dries, and when it's cut down, it's put in a kiln, and then it dries further when it's inside your house. So to understand whether it's going to be stiff enough and straight enough for the applications you're looking for. This is the first of its kind, the only one of its kind in the world. So we've had a few trials and tribulations along the way. There's probably been 6 or 7 years of development that's given rise to the DiscBot. So some of the particular measurement techniques came around almost in a serendipitous manner. For example, the spiral grain measurement really was an accidental discovery where a colleague wanted an image of a disc for a presentation. He put it on a flatbed scanner with the writing on the top surface, and he actually found that the writing appeared in his image. And he thought, no, that can't be right, I must have it the wrong way. So he went back, checked the disc, no, it was correctly orientated, but the light was able to shine through the disc and pick up the writing on the top surface. And then we realised that actually the light is following the grain. So if we cast a shadow through the disc, if the grain is straight up and down, the shadow should actually appear immediately behind the object that's casting it. If the shadow appears to the side, that is a measure then of the grain angle. And we're able to take that, develop it further, and come up with a completely new method for measuring spiral grain in wood. So it's a really quite neat story of invention. One of the things we really want to be able to do is understand what is a good phenotype, what kind of tree is going to produce wood products that are considered superior. And so if we can actually apply some of the techniques that we've developed with the DiscBot to trees that are in the breeding population, for example, in progeny trials, we can actually then understand what a really good phenotype looks like, and we can actually then select and breed for it. It's one of a kind. It's that simple. It's the only one of its kind in the world. Certainly when we've shown it to people in other groups around the world, their jaws have dropped and said, we need to have one of these. So I think, the team, the people that have worked very hard on it to make this machine can take a huge amount of pride in developing something that no one else has.
Council brought in the Wood First policy. It was adopted a few months ago, and it's very important to the principles of our region, ensuring sustainability going into the future, and wood is definitely a very sustainable product. It's been in our region for thousands of years, but recently it's radiata pine is the commercial wood that's been planted in our district, and the main thing for the radiata pine was to actually mitigate erosion. So from council's point of view is that we take a leadership role in leading our community's built environment by using wood. And it doesn't really matter what wood they use, whether it comes from overseas or New Zealand. The main thing it is a sustainable resource, legal of course. So radiata pine in our district and the native timbers that were milled a few years ago, they are starting to surface nowadays, and they are used for furniture and that. So we have the support of the Eastland Wood Council, support of our construction firms, support of our whole community in using wood as a sustainable product, and that's why we become Wood First. And so when we talk to our architects, we make sure that they use as much wood as possible and practically in terms of engineering strength. And by all accounts, I know that wood is a very strong product. It has good properties that surpasses steel, like is more fire resistant than steel and stronger than steel. It doesn't mount like steel. So we specify those at the beginning, because when you start to specify wood in the beginning, it actually probably ends up to be similar price, if not cheaper at times.
And there are other local bodies now looking at the same policy, and we await the same from our central government. That's Forest Call for this week. Ka kite, and time to look at what we have along for next week. Next week on Forest Call, we find out the details of the biggest deforestation proposal in New Zealand's history. A lot bigger than the 1 billion trees. All for the purpose of sequestering millions of tonnes of carbon emitted by industry and livestock into trees to do New Zealand's bit to fight climate change.